Section: Introduction. In this section, we discuss monocular depth estimation, which has been widely applied in various tasks like image editing, scene reconstruction, and robotic navigation. This task is challenging due to the ambiguity between scale and distance, requiring learning-based methods to use strong semantic information for better performance. Recent approaches have adapted large diffusion models for depth estimation by framing it as a conditional image generation task, leading to impressive results with high detail. However, the general consensus is that these models are slow because they require multiple evaluations of a large neural network during inference. We argue that, contrary to popular belief, models like Marigold can produce reasonable predictions with just one inference step. Our investigation reveals that Marigold's poor performance in few-step scenarios stems from a significant flaw in its inference process. While this issue has been noted in the broader diffusion model literature, we show that it is especially critical for image-conditional methods like Marigold. Our findings suggest that previous works may have reached incorrect conclusions based on flawed inference results. By correcting this inference flaw, we find that Marigold-like models can achieve single-step performance comparable to multi-step methods, while being over 2002 times faster. This fix allows diffusion-based depth estimators to compete with state-of-the-art discriminative models in terms of speed, paving the way for further enhancements. A single-step model enables efficient end-to-end fine-tuning without the need for multiple network evaluations. Additionally, we can now apply advanced techniques like self-training with pseudo-labels to diffusion pre-trained models effectively. We fine-tune Marigold into a deterministic depth estimator for monocular images using a scale and shift invariant loss function. Surprisingly, this model outperforms the best configurations of Marigold. We replicate this with surface normal estimation and observe similar outcomes. End-to-end fine-tuning with a specific loss function surpasses more complex architectures trained on larger datasets. Following Occam's razor, we find that even the simplest approach, directly fine-tuning stable diffusion into a deterministic model, outperforms Marigold and other diffusion-based methods. These results challenge earlier conclusions, showing that diffusion-based methods do not have to be slow and that framing depth estimation as conditional image generation is not necessarily more effective than straightforward fine-tuning. However, we confirm that a small dataset of high-quality labeled data is sufficient for good performance. In summary, our contributions include analyzing Marigold and similar models to identify a critical flaw in their inference pipeline, fixing this flaw to enable efficient single-step inference, and demonstrating that simple task-specific fine-tuning is effective for depth and normal estimation. We validate our approach on common benchmarks, where our deterministic one-step model outperforms other diffusion-based methods and achieves results comparable to state-of-the-art techniques for depth and surface normal estimation. In the related work section, we note that several recent generative methods focus on producing multi-view depth and normal maps but are limited to single-object scenarios, making them unsuitable for complex environments. Other approaches have used diffusion models for scene-level depth estimation, but they often struggle with generalization. Marigold, which fine-tunes stable diffusion to generate detailed depth maps from images, relies on high-quality synthetic datasets and a smooth transition in the latent space. While Marigold has inspired follow-up works, many still face high computational costs during inference due to iterative processes. We observe that most models, except for Depth-FM and Marigold LCM, suffer from flawed implementations that hinder their performance in few-step scenarios. Moreover, we find that the denoising diffusion fine-tuning objective used by Marigold and its successors is not as crucial or beneficial compared to task-specific end-to-end fine-tuning. Section Summary. In this section, we discuss the advancements in monocular depth estimation using diffusion models, highlighting a critical flaw in the inference pipeline of models like Marigold that affects their performance. We demonstrate that with a simple correction, these models can achieve efficient single-step predictions comparable to multi-step methods, and we find that straightforward task-specific fine-tuning yields superior results over more complex architectures. Section: Image-Conditional Latent Diffusion Models. In this section, we review conditional latent diffusion models and how Marigold utilizes them for depth estimation. We also discuss why single-step inference should yield reasonable predictions for depth estimation and why this has not been the case in practice until now. Latent diffusion models, LDMs, work by learning to transform a simple noise distribution into a data distribution through a process that adds small amounts of Gaussian noise. The noise added at each step is kept minimal, allowing the reverse process to be approximated as Gaussian as well. We ensure that the number of steps is large enough so that the final distribution can also be approximated as Gaussian. The forward process can be described using a data sample, and for the reverse process, a neural network is trained to gradually remove noise to predict the original data from the noisy input. An alternative method, denoising diffusion implicit models, DDIM, allows for inference in fewer steps while maintaining the same training goals as DDPMS. LDMs operate in the latent space of a variational autoencoder, VAE, which consists of an encoder that compresses inputs into lower dimensional codes and a decoder that reconstructs the original input. This setup makes LDMs easier to train due to the reduced dimensionality and smoother latent space. In conditional diffusion models, both the forward and reverse processes depend on additional inputs, like text descriptions or images. The network is trained to denoise the input based on this additional information. It has been shown that the best prediction at the final step is the average of the data distribution. For unconditional and text-conditional image generation, this average can result in blurry images. However, for image-conditional generation, such as depth estimation, we expect the distribution to be more focused, leading to a single depth map. Thus, the optimal single-step prediction should closely match the true depth or normal map. Marigold approaches depth estimation as a conditional latent diffusion process, building on large pre-trained models like Stable Diffusion. Since Marigold is conditioned on images, we anticipate its single-step prediction to be a reasonable but blurry depth map. Next, we analyze Marigold's behavior during inference. We observe the pixel-wise standard deviation across steps for Marigold's default 50-step inference and find minimal differences, indicating that the model's predictions change very little during this process. However, we notice that the single-step output resembles pure noise rather than the expected first step of the 50-step schedule. This issue arises from a flaw in the inference scheduler used by Marigold, which leads to inconsistent pairings of time step and noise, resulting in nonsensical predictions. To resolve this, we need to align the time step with the noise level. We can implement a trailing setting, as suggested in recent work for image generative models. While this adjustment had minor effects on image generation, it is crucial for single-step inference in models like Marigold. We compare the outputs from the flawed and fixed inference schedules and clearly see that the fixed process yields sensible predictions, while the original does not. Section Summary. In this section, we review how Marigold utilizes conditional latent diffusion models for depth estimation and discuss the challenges of single-step inference, which has previously led to nonsensical predictions due to a flaw in the inference scheduler. We demonstrate that aligning the time step with the noise level is essential for producing accurate depth maps in single-step predictions. Section: End-to-end fine-tuning of LDMs. In this section, we discuss the end-to-end fine-tuning of diffusion models for depth estimation. While these models generally perform well and capture details accurately, they can produce artifacts like blurriness or excessive sharpness. This issue may arise from the training objective, which focuses on denoising rather than the specific task we want to achieve. To address this, we fine-tune the diffusion model directly in an end-to-end manner. We recognize that fine-tuning without effective single-step predictions would require complex backpropagation through many network calls, which is impractical for large models. Therefore, we continue training the modified UNet from the diffusion training phase but fix the time step to a specific value to ensure single-step predictions. We also replace the noise with its average value, which is 0, and only pass the RGB latent through the model. During training, we aim to transform pure noise into a clean depth prediction. The output from the UNet can be turned into a latent depth map, which we decode using a fixed VAE decoder and compare to the actual depth map. Our approach differs from Marigold's method, which focuses on matching latent representations using a mean-squared error loss. Instead, we optimize for accurate decoded depth maps, resulting in a deterministic feed-forward model trained with a task-specific loss. For monocular depth estimation, we utilize a loss function that is unaffected by global scale and shift, fitting the predicted depth to the ground truth to determine these values. For surface normal estimation, we base our loss on the angle between the actual and predicted normals. In terms of implementation, we use the official Marigold checkpoint for depth estimation and train a model for normal estimation using the same setup, encoding normal maps as 3D vectors. We adhere to Marigold's hyperparameters, which performed well in our tests. We train all models for 20,000 iterations with the Atom W optimizer, starting with a learning rate of 3 × 10⁻⁻5, and apply exponential decay after a warm-up period. Our batch size is 2, with gradient accumulation to effectively handle a batch size of 32, allowing us to mix images of varying aspect ratios and resolutions. We use a combination of indoor and outdoor scenes from HyperSim and Virtual KITTI2, which enhances model performance. Fine-tuning takes about 3 days on a single NVIDIA H100 GPU. Our fine-tuned models outperform most current state-of-the-art generative methods for depth estimation across various datasets. Among discriminative methods, only Depth Anything and Metric 3D show better performance, but they were trained on significantly larger datasets. For surface normal estimation, our fine-tuned models achieve new state-of-the-art results on all evaluated datasets, except for NYU v2, where Metric 3D v2 remains the leader.